All right, so let us begin with the recap from the previous episode of Hurwitz's theory, right? So yesterday we talked about the degeneration formula, which is something that at this point you should have gathered that, a lot of us really love and find important, and is maybe one of the key ideas that drives all of the technology that's been developed. And we've seen in particular how the degeneration formula is a very natural geometric fact that implies the correspondence theorem between tropical and algebraic Hurwitz numbers, right? So just really it's a very satisfying explanation for this correspondence theorem. And then through the degeneration formula, one can actually generalize the notion of tropical Hurwitz numbers beyond this special case of double Hurwitz numbers to you can really, do tropical Hurwitz number with arbitrary genus of the base, arbitrary ramification profile that you ask, and you get these nice, beautiful, complicated, confusing graph counts that are weighted, but these weights do need, in the case that you go beyond double Hurwitz number, you're going to need some geometric input data. Some of these multiplicities, some of these vertex multiplicity you need to count these graphs with are now triple Hurwitz numbers, and triple Hurwitz numbers are not seen in any way by tropical geometry. And so you have to sort of feed them in, right? And so in a sense, tropical geometry will tell you okay, if you know triple Hurwitz numbers, I will organize for you the degeneration formula in a very natural way so that then you can sort of unravel the combinatorics in a natural way. Cool. Any questions or comments so far? No? All is clear, or all is already forgotten from yesterday? What are you talking about? Okay. All right, so today for the season finale, we're going to try to realize, we're going to succeed in realizing double Hurwitz numbers as intersection cycles on moduli of curves. Okay? So we've seen Vance has convinced us by shaving his beard that, it was very important to realize simple Hurwitz numbers as intersection number in the modular space of curves. Otherwise, he would not have shaved if it wasn't that important, right? And so today we're going to try to do the same with double Hurwitz numbers, right? And let me say, a couple more reasons why double Hurwitz numbers are special. The first reason has to do with this moduli space that we use to produce cycles that are then double Hurwitz numbers, and this is the Francesca's rubber relative stable map moduli space, right? So if we start with a moduli space M, G, P1, x plus 0, comma, x minus infinity, bar, squiggle. Okay, so this is the rubber moduli space of rubber stable maps to P1. Again, think that generically, right, what this means is you have coverings of P1 by genus G curves where you specify the ramification over 0, you specify the ramification over infinity. You say nothing about everything else, and you declare two of these covers isomorphic if they differ by a scaling of P1, right? Really an action on P1 that is x goes to alpha x or lambda x for lambda non-zero complex number. That's why it's rubber, right? Because you're kind of thinking of this P1 here as you can, stretch it or not. And, any maps that differ by stretching the inside of the P1, right, are going to be considered isomorphic. Okay. So this is a moduli space that we've used, right? It's got a branch morphism. The degree of this branch morphism is double Hurwitz numbers, but it also has a source morphism, a map into mg n bar, where g is the genus of the curve, and what is n? Well, n is the number of these points where I have special ramification that I can decide to remember. Right? And all of a sudden, what I see here, if I forget the map and if I forget the P1, is a genus 2 curve with 5 mark points. Okay? So there's a natural map. Let's call it pi. Let me actually write it here. No, let's not call it pi. Let's call it mu. I don't know why. For stabilization. It's like E for Hodge. mg P1 x plus 0, x minus infinity, to mg n bar, where n is the length of the vector x, right? And so what we can do, right, is we can push forward this space here. And you should be like, what does push forward a space mean? Well, we'd like to say, well, this space has a fundamental class, and you push, that's a cycle, a zero dimension, a degree 0 cycle, you push that forward. And I would say, well, but this doesn't have a fundamental class because it's ugly, it's singular, it's not equidimensional, and so on and so forth. But well, Francesca told us that you can put a virtual fundamental class. So now we're good to go, right? So what we can do is we can consider the push forward of the virtual. Now let me erase the picture here. Fundamental class of this space. And this is a cycle. Well, it's actually a cycle class in mg n bar, right? Which has a name. This is called the double ramification cycle. drgx. And this cycle class has been studied and has many amazing properties, right? One of which is polynomial. In the xi's of degree 2g. And another one is that there is a formula for it. It's a graph formula by Pixton. And this formula is simultaneously extremely beautiful and sort of like a little bit of a Wizard of Oz kind of formula, in the sense that it's like, click your heel 3 times and say there's no place like the double ramification cycle, and here it comes. It's really beautiful in the sense that it's obtained as a sum over all possible dual graphs that might arise from this problem, and all dual graphs are weighted in a way which is purely local to the combinatorics. So that's amazing, right? But the weird thing is that once you do this weighting is, have to prove that this weighting gives polynomial weights, and then you have to take some sort of you have to evaluate this polynomial, which is kind of weird, right? But nonetheless, this formula has been proven, and so we actually have access to this cycle as a tautological class on the moduli space of curves with very nice properties. The second reason, so this is one reason why double Hurwitz numbers are special. The second reason why double Hurwitz numbers are special is that another way to think about maps, the picture that I raised, maps to P1, where you specify the ramification profile over 0 and infinity, is thinking about curves of genus G with mark points, such that the divisor you obtain by taking the linear combination of the mark points that you have with this weight being xi, this divisor is principal. Because being principal means that there is a rational map, but the rational map is a map to P1. So it's kind of a very, sort of silly logic, but, like the interior, so this space, the rubber relatively stable map space that we're talking about is a compactification of a locus of principal divisors on curves. Okay. Which in a sense it means that there is a connection between double Hurwitz numbers and theory of like Jacobians and a whole other like party town in algebraic geometry. Okay? Cool. All right, so maybe I have motivated why I want to go back to double Hurwitz numbers. Our goal is to cut down the double Hurwitz number as a sort of the degree of some intersection cycle on the modulo of curves. I'm going to do it in two ways. In the first way, I'm going to be very fast and again, leave it to Vance again to fill in a lot of the things that I'm not going to say. Which is, again, there's a tautological diagram that we can exploit, right? So I have my space of rubber relative stable maps. And it has two tautological morphisms, mu to mgn bar and br to m0 2 plus r epsilon mod sr. Okay. And we've already seen that we can express the double Hurwitz number as take the class of a point and pull it back. And you get a zero-dimensional cycle whose degree is precisely double Hurwitz number. Now, if I want to express the double Hurwitz number as the degree of a zero-dimensional cycle in mgn bar, there is one absolutely silly thing they can do is I take this zero-dimensional cycle and push it forward. Ha-ha, it's an mgn bar. Okay? All right, not very satisfying because even though I have a zero-dimensional cycle in mgn bar, it really is just the image of some zero-dimensional cycle here, and everything that I need to do to cut it down has to do with this side of the diagram, nothing there. Right? So if I wanted to express the zero-dimensional cycle out here, somehow like more in terms of the tautological geometry of mgn bar, one thing I can do is to use a special way to cut down this class of a point, and is use what we already kind of glimpsed at is psi classes. Okay, so that's why I think you're talking about psi classes tomorrow, right? Yeah, of sorts, right? So again, let me draw Vance again. Okay, so psi classes. We have, actually, let me draw a picture here of okay. So what's this? There is my there's a general element in my moduli space of relative stable maps. If I just forget the top and look at the bottom, I see my element in the Lose-Manin space where I kind of keep track of the various branch points. And if I forget the cover and stabilize, I get my image via the stabilization morphism. Right. And notice that when I go to mg and bar, I might have some components of my curve that all of a sudden are no longer stable, right? Because if I had a cover here that's ramified only over the red point and the node, when I forget the map, well, then this component has only two special points and it should go. Which is okay, you contract it and the special points falls here. Okay. Now, psi classes, we've introduced them briefly, and really the only thing I would like you to think about right now is that they're classes constructed from line bundles on moduli spaces, and these line bundles have really the fibers have to do with cotangent lines of the objects parameterized. Right? This is also in general like a key point of the philosophy of doing geometry on moduli spaces is you study geometric objects on moduli spaces that are described by geometric objects on the objects parameterized. What did I just say? Right? A moduli space of curves is a very complicated thing, right? And so studying something like the tangent space of the moduli space of curves or the tangent bundle of the moduli space of curves is in principle studying something very complicated on something higher dimensional, on something, stacky, like very complicated. But one way that we understand this is saying, look, the fibers of the tangent bundle of the moduli space of curves are cohomology groups on the curves themselves. Right? And so now you go, woohoo, I've done Riemann-Roch for curves. I know that theorem. And all of a sudden you can compute the dimension of mg. Right? That's the amazing trick, right? So in a sense, psi classes is an example of this similar yoga, right? These cotangent line bundles are line bundles on moduli space of curves, which are very, very complicated. But the way we understand them is saying, well, for a point in the moduli space that corresponds to a particular curve, the fiber of this line bundle gets identified with a line attached to the curve parameterized. Questions, comments? Okay, so if you accept this as a philosophical statement or a meditation point or something, right? Then we have three moduli space here, and each moduli space has their own psi classes, right? And so in particular, I'm going to have a psi class on this target space. I'm going to call it psi hat. That somehow has something to do with this tangent line. Right? I have a psi class on this moduli space corresponding to this point. I'm going to call it psi tilde. And I have a psi class on mg and bar that has to do with this cotangent space. I'm just going to call it psi. Okay? And so here are some facts. So the first fact is that if you take an appropriate power of this psi hat, you get some multiple of the class of a point. And this fact is really almost trivial. Really all I'm saying is if you intersect psi naught with itself the right number of times, you don't get zero. But you actually get some number of points, and you know what this number is. So you can express the class of a point as a multiple of psi hat to the appropriate power, r minus 1. Right? So psi 0 hat to the r minus 1 is a non-zero multiple the class of a point. So far, so good. This is not shocking. Second fact that also should maybe not be too shocking is that psi naught hat and the psi tilde for the point living above it are not unrelated. In the sense that for every point in my moduli space, this point right here is a point of ramification order xi over x naught, which means that the local analytic expression for the map around this point is z goes to z to the xi, which means that if you go and look at the tangent spaces and the transition functions for the tangent spaces, there's going to be like the tangent space here is always the xi tensor power of the tangent space here. Which in particular means that if I burr up a star psi naught hat, what I get is xi times psi tilde. And the third fact, and again, I think Vance will give you some incarnation of this fact, even though maybe not exactly this one, concerns the relationship between the psi classes here and the psi classes here. Okay. So notice that if instead of this point, I had taken any one of the other 4 points, right? Then the tangent space of this curve is exactly the same as the tangent space of this curve. Right? So almost everywhere, the tangent line at mark point here is the same as the tangent line of the mark point here. The only place where it differs is when the tangent line here is on a bubble that gets contracted here. What this is saying is that we can identify the fiber of the two line bundles on the moduli space on the complement of the codimension 1 locus where this point is supported on a contracted bubble. And so when you can identify the fiber of two line bundles of a codimension 1 locus, you also know that the two line bundles are isomorphic up to tensoring by some power of that divisor. And okay, we have to be careful. If this divisor is not reducible, like some linear combination of O of di's, right? But this to be said that, again, there's a relationship with the psi class here and the psi tilde class here. And this is precisely of the form, so the mu upper star of psi is equal to psi tilde minus, let me say d, and d is, roughly speaking, the divisor in the moduli space parametrizing curves where the ith point is on a trivial cover. Right? Where by trivial cover, I mean a cover that is only ramified over 2 points, and so when you stabilize it, it disappears. And now, if you're happy with these 3 facts, you might see how I might want to compute double Hurwitz number as a natural intersection cycle on mgn bar, which is, let me start by expressing the class of a point as a power of psi naught hat. Oh, is there a question? Oh, yeah. What is the isomorphism? It's just that the tangent, there's a map from this tangent line to this tangent line, right? Which is just x goes to x, sorry, z goes to z to the xi, which then you differentiate it, right? And that should tell you that you can express this line bundle as the xi tensor power. Huh? Yeah. But I mean, yeah, okay. you're right. The differential is 0 at that point, right? But I mean, you actually have, what am I saying? That you have a line bundle, and because the map is such, when you have a transition functions from the line bundle down here, you just get that cocycle to the xth power, and that gives you the right thing. Anyway, I can point you to the paper where it's written. Like it's, I mean, this is I haven't prepared for like a careful proof of this stuff because I don't think it. I mean, it's a technical thing. I mean, I can tell exactly where to find it if you're. But that's the fundamental fact, right? That at every point, kind of the relationship between local neighborhood here and local neighborhood here is always fixed and it's always the same, and that relationship you can translate it to like a relation about the cocycle and tangent bundles. Okay. So coming back to the more or less technical part, in a sense, once you have these three facts, that to make each of these honest, you have to work a little bit. You may express the class of a point as a power of psi naught hat. Then you pull it back via Burr, and that becomes a power of psi tilde, but with some xi there. And then you may use the projection formula, right, to say, okay, well, these psi tildes, I can write them as mu upper star of psi plus some divisorial correction. And then you the projection formula to put that product into MGN bar. And what you end up doing is expressing the double Hurwitz number as a combination of evaluation of psi classes on boundary strata of MGN bar, capped with the restriction of a virtual fundamental class of the space of relatively stable maps on the boundary strata on MG, and so on and so forth. And anyway, it's a whole big mess, but again, from this fact and from how the virtual fundamental class of a moduli space restricts to its strata, you actually can conclude, you can actually witness the local polynomiality of double Hurwitz number. And in fact, you witness the wall crossings as a sort of transition of psi classes. Because when you go across a wall, some of these bubbles might disappear. Right? Just in a very similar way to what happened in the tropical case. Okay? Cool. Any questions so far? This is one way to obtain the double Hurwitz numbers as an intersection on MGN bar, but it's not the most interesting way, right? So I want to spend, I have another half an hour, I'll be right there in a second. I want to spend the last half an hour to show you like a way that makes a much better connection to what Dhruv and Hannah have been talking about, and also allows us to go further, allows us to go beyond. Yeah, Frankis.
So how do we know which xi? So
yeah. Good question. You can pick. In fact, this gives you multiple formulas if you want. Right? You can pick, psi naught hat, or you can pick psi infinity hat. That's your choice. And you can pick whatever you want above here. Yeah.
So technically it would be psi tilde sub pi.
So I mean, I've really, I mean, I have not put any decoration here because I only wanted to decorate one point, but each point has its own I, right? Yeah. So here, I mean, in a sense, there's something like cool here that you can make a bunch of choices and they're all going to give you like the same answer, right? I don't know that anybody has tried to explore what happens when you play these formulas one against the other for different choices. But again, this got a little messy. By a little, I mean a lot, right? So I don't know. But I mean, yeah, okay. No, I want to preserve 29 minutes for the rest. So yeah. No. More. All right. So take 2. And let me first build a roadmap. Okay, so if you want to compute a double Hurwitz number, okay, so we've seen that we get an associated interesting cohomology class in MGN bar, this thing called the double ramification cycle. We've also seen that we get a tropicalization of the problem, right? So we get a tropical Hurwitz number, but its tropical Hurwitz number comes from a tropical moduli space moduli space of tropical covers. Okay? Now, this moduli space of tropical covers has a relation with, through what Drew has referred to as, magical positry. Right? So there's some very high mountains with clouds, right? And if you're willing to climb through the mountains or through the clouds of magical positry like Drew did, you will come out with this tool, right? That will allow you to, and I'll, again, if I have a little bit of time at the end, maybe I'll say a few more words about it. But that will allow to use the moduli space of tropical covers to construct a birational modification of the moduli space of curves. And it will also provide you with a natural cohomology class on this birational modification, so that now what you can do is you can take the proper transform, of this cycle, and you intersect it with this, or you evaluate again this natural cohomology class, and out comes the double Hurwitz numbers. And voila. Okay? So that is the roadmap. Okay, so what I want to do is I want to take my time to illustrate this roadmap in one very specific example. So hopefully it will kind of make sense, right? And then, the theorem will just be like this specific example actually generalizes, right? So that's the theorem. Cool. Okay, so let's think about the double Hurwitz number h 1, 3, minus 3, which at this point we have several ways to compute this to be the number 2. Okay? Yeah, okay. So r equals 2. And let's start drawing some sort of cartoon pictures for the relevant characters here, right? So first of all, we have a moduli space of rubber relative stable maps to P1. This moduli space is one-dimensional and it has 2 components. I have to be careful with my colors because I have a finite number of colors. So I have so let me first say this is going to be the M1 P1 3 0 minus 3 infinity bar rubber. And I have a blue component that parameterizes sort of like nice covers for smooth P1s. Sorry, from smooth genus 1 curve to P1 with 2 special points. I have 2 more ramification points. Here they are. Right? And so I have really 4 points moving in a one-dimensional target, mod PGL2, that's a one-dimensional space. And then I have another one-dimensional component. Let me draw it in red. We're corresponding to maps where I have just a rational curve mapping to P1, z goes to z cubed, so it's only ramified at 2 points, and a genus 1 contracted component. Okay? Here. So far, so good? Cool. And this is also dimension 1 because I have a 1 parameter family of choices for the elliptic curve, right? And I have no choice. I mean, the map from the genus 0 curve is just z goes to z cubed. And you might think like, well, I have a choice of where to attaching this genus 1 curve, but up to rubber, they're all isomorphic. It's one dimensional. Cool. Then on the algebraic side, right, if I look at my source morphism, I'm going to map into M12, right? I have genus 1 curves with 2 special points, namely the inverse images of the 2 branch points. Okay, so let me also draw a cartoon for M12 bar. This is a 2-dimensional space, again, whose general point parameterizes genus 1 curves with 2 mark points. It has a codimension 1 divisor I'm going to call sigma that parameterize curves where one and 2 are on this on a rational component, right? And it has another divisor called delta naught that parameterize curves where the elliptic curve degenerates to a nodal rational curve. And the points 1 and 2 are on this rational component. And then I have two, could I mention two strata, two zero-dimensional strata, right? Namely the intersection of delta naught and sigma, where it consists of the unique curve, the unique sort of rational nodal curve with attached another rational curve with 1 and 2, and another zero-dimensional strata corresponding to what's called the banana curves. So the genus 1 curve has split into two rational curves attached at 2 points. Each of these points is supporting one of the marked points. Okay, so if you've seen this picture before, you probably, it felt good. If you've never seen it before, this might be like a little bit fast, right? But the key point is like, if you copy this down and then look at it for long enough, you'll recognize that this is the posted stratification of M12 bar. Okay. So far, so good. Questions, comments? No, we're good. Cool. So then I want to, on this other half of the board, I want to put the tropical analogs of this thing, right? So I want to look at the tropical moduli space of covers, right? And this has two cones. One is one-dimensional, and the other one is two-dimensional. The one-dimensional cone is parametrizing good, honest tropical covers of the ones that we've talked about before, right? I start at 3, I end at 3. I have two trivalent vertices. Great. My vertex parameterize the tropical cover where the 2 points have come together, and so instead of like a loop, I see a vertex of genus 1. So this vertex parameterizes. And this red cone parameterizes covers which are a little bit weird, because really what's happening is the interior of this cone. Is like, actually, let me draw this in black. And all that I've drawn in red is contracting down to a point. And why is this a tropical cover? Well, it depends on how you want to define tropical covers, but somehow if you want to mirror the situation in the algebraic world where you have this kind of somehow pesky component that with things that are contracted, that you might say, well, I'm going to allow contracted subgraphs as well. And what we'll see in a second, that in a sense it doesn't matter. All we've done so far in talking about Hurwitz numbers has been ignoring both this component and this component, and everything goes through the same way, and hopefully I will show you why. Okay, and so we also have a tropical source morphism that forgets the cover and only remembers the tropical curve, and this maps into M12 trop. M12 trop is a two-dimensional cone complex. Consisting of one vertex, two rays, and two two-dimensional cones. Let me start drawing the vertex. The vertex corresponds to a tropical curve that has one vertex of genus 1 and 1 and 2. Let me color code the rays. One ray corresponding to a genus 1 vertex with a tripod. Right? And y is, you should think of it as the length of this edge. Another ray corresponding to a loop, a vertex of genus 0 and the two ends, and you should think of x as the length of this loop. And then I have a two-dimensional cone sort of in between these two rays, right, corresponding to an armless sleeping stickman. And this is your x and this is your y. So I have two lengths to assign. And I have another two-dimensional cone that gets folded so that both rays are the green rays. So I'm going to draw this diagonal, but you should think that I start with a cone and then I fold it, right? And this is sort of the candy tropical curve. 1 and 2. Let me say this is x1 and x2. Right? And now you see that, in principle, you can choose arbitrary lengths for x1 and x2, so you have a two-dimensional orthant of choices. But then if you choose x1 to be 1 and x2 to be 3, and I choose x1 to be 3 and x2 to be 1, we're actually picking isomorphic tropical curves. Okay, again, if you've seen M12 trop before, this is like old music. If you haven't, you might need to, record this picture and ponder it a little bit more. But one thing that I hope you can already immediately see, even if you're not familiar with these pictures, is that even the way I've color-coded things, right, highlights sort of the bijection between the stratification here and the stratification here. Right? Because I have a unique two-dimensional open stratum here in black, right, that corresponds to the vertex. Right? So it's a inclusion reversing bijection. Right? Then I have two codimension 1 strata, green and red, and I have two one-dimensional cones that I drew in green and in red, because if you look at the little topological picture that I drew here for the topological type of the curves parameterized by these divisors, and take the dual graph of this topological type, we'll see precisely that this tropical curve is the dual graph of this, and this one is the dual graph of this. Is there a reason why I drew the red line horizontally here and vertically here? Yes, but I'm not telling you. But if you're curious, and vice versa, vertical and horizontal, yes, but I'm not telling you, but if you're curious, let's talk about it. And then finally, my my codimension 2 strata correspond to dimension 2 cones, and again, we have the dual graphs of the corresponding topological type tell me which to associate to which. Okay. You do a time check here. Any questions, comments? I haven't done anything yet other than setting up all the characters that are going to come into play. Okay, so in a sense, all we've done is this first red arrow. Okay. Now the next thing I need to do is, well, I'm going to set up my DRG thingy, which means I need to look at the image of the virtual phenomenal class of this moduli space in here. It actually turns out this is a really special case because I have no components of x's dimensions, so the virtual fundamental class is the fundamental class of this thing. Great. So I just have to look at where this space is sent, right? And this red component is mapped all inside this divisor, right? Because I have elliptic curves together with a rational bubble, and the 2 points are in the rational bubble. And this blue component, it's mostly sent out into the two-dimensional orbit, right? But what happens when these black points want to collide with the red points? What are the boundary points of this blue component? Well, if the black points want to collide with the red points, we don't let them, right? We send them off each on their own component. And now if you see, if you say, okay, what can I put here on top of this picture, all I know is that I have to have a triply ramified point over the red points. I have to have only one transposition, and then I have to go find something that kisses. Right? But well, by cut and join equation, if you start from a 3-cycle and hit it with a transposition, you can only open a cycle. It's only the 3-cycle, and you can only open it into 2 plus 1. Right? So really what happens is that you get something like this. My 2 points, 1 and 2. So it's 2 rational curves attached at 2 points. And so if you forget the map and just ignore all the things that had to do with the map, all you see is 2 rational curves attached to 2 points, each with its own point. Well, you're exactly the banana graph. So what's happening is that the second component goes through this codimension 2 boundary stratum. Okay? And this is something that upsets Drew very, very much. Right? I mean, I'm glad he's behaving right now. Yeah, he's scowling, but right? Why? Because I have a one-dimensional moduli space, or one-dimensional object, inside a 2-dimensional stratified object. Right? And what Drew likes is that the way that if you pull back the codimension k orbits from the big space onto your thing, you get codimension k orbits in the little space. Right? So you pull back a codimension 2 orbit in the 2-dimensional space, you should get a codimensional 2 orbits in the 1-dimensional space, which means you should get nothing. Right? A curve should miss a point in the plane. Right? If you had too much to drink one night, right, and you just toss a curve into a plane, it's not going to hit your favorite point in the plane. It's going to miss it. Right? So this is somehow a really non-general behavior of this map of moduli spaces. It's something that we need to fix. How we're going to fix it? We're going to ask tropical geometry to do it for us. Okay, so we go back on this side and say, okay, well, let's see what happens on the tropical side with the corresponding stabilization morphism, right? And well, what we're doing right now is we want to record the location of the 2 branch points. No, sorry. Forget what I said. That's coming in a second. That's for the cohomology class. The stabilization morphism is cool. So this red cone somehow gets mapped to this whole 2-dimensional cone. And this blue cone, this is a 1-dimensional cone, it's a ray, right? And this gets mapped inside this cone. But in this cone, I can choose the lengths of the 2 edges arbitrarily. Whereas in this ray, I can't. This downstairs edge must always be twice as long as this upstairs edge. Right? Because then they need to map. When you map 2 times this length should be the same as 1 times this length. It needs to satisfy an equation, right? So this is a ray with slope 2 or 1/2, depending on how you orient yourself, right? Inside this 2-dimensional cone, right? And so if you remember, an hour ago, Drew told us, right, if a cone maps inside a large dimensional cone, we don't like it. And we don't like it because it precisely is telling us that this sort of atypical behavior is happening. Okay? And so what do? We say, okay, if we were in toric geometry and we started with a cone, 2-dimensional cone, and then we subdivided to rays, toric geometry would tell us, oh, all you're doing is you're blowing up a point in that surface. Okay? And somehow, kind of the magic of this technology is like, well, you can actually do the same thing. You can sort of pretend that you're locally toric, and so what this is telling you is blow up the corresponding orbit. And sometimes the birational transformation might need to be more complicated than just a simple blow up. Even here, it's actually a way to blow up. Let's, again, let's hide the technicalities for a second. But so this ray right here is telling us we should blow up this point. Okay? And when we blow up this point, what happens, let me actually redraw the picture right here. I've now obtained that my one-dimensional blue moduli space intersect a one-dimensional stratum of this new moduli space in a point, and it misses all the two-dimensional strata, right? Which is good. It's a good behavior. Notice I drew this as a little tangent because I'm not saying that necessarily that this intersection needs to be transverse, but it's dimensionally transverse. Okay? And so now we're almost there. Now we're saying that, okay, we need to use this geometry to kind of compute the double Hurwitz numbers, right? And so to compute, yeah.
You don't need the green in the picture to do this. Don't we want every lesson?
I don't know, but I mean, it's I'm not gonna care. That's, I mean, the thing is like, I'm gonna tell you what to intersect the blue curve with, and it's not gonna be the green, right? So I mean, what really like, if it means the green, it means the green. That's okay, right? I mean, huh? I mean, I think if you miss completely, that's okay, right? I mean, it's still transversal, right? I mean, I could probably like stop for 45 seconds and tell if it hits the green, but let's yeah. All right, to compute the double Hurwitz number, we get a cohomology class from the tropical branch morphism. And so again, let's think for a second about, we've drawn the tropical source morphism, right? We now want to take the tropical branch morphism I'm drawing the target of a tropical branch morphism as a one-dimensional ray, because even though I have 2 branch points, everything is defined up to translation, right? So I can always assume that the first one is at 0 and the other one is to the right of 0, up to translation, right? So I really need to evaluate only the second point. And now what I see is that this whole red cone all gets squished down to a point. And this blue cone, well, it gets spread out down here. Okay. And again, now I can't really get away with using the word piecewise polynomials, right? So from, again, toric geometry, you might know that piecewise polynomials on the fan of the toric variety give you equivariant cohomology classes on the toric variety. If you don't know it, I just told you, right? But anyway, there again, this is yet another part of this sort of combinatorial dictionary. It's like you figure out something about the geometry of the toric variety from the combinatorics of the fan. 2 minutes over time. Okay, so from toric geometry, piecewise polynomial functions on the fan give you something geometric. Part of that magical positry, again, extends this to this log world, right? So if I want to get a way to get a natural cohomology class on my log space is to start from a piecewise polynomial in the tropical thing. So what I'm going to do is I'm going to take precisely the polynomial t here. The polynomial t, again, not so secretly once you understand what this piecewise polynomial correspondence means, is like taking a class in the laws of Manin, which is the class of a point. When you pull it back, first of all, you see that you get something which is identically 0 on the red cone, and so the red cone doesn't matter. Then you get a polynomial here that gives you a class that corresponds up to some multiplicity to this exceptional divisor right here. And so the Hurwitz number is going to be obtained by intersecting this double ramification cycle, which consists of the union of the red and the blue line with essentially this exceptional divisor right here. And then you have to go and compute some multiplicity of intersection. And what you see is that the multiplicity is exactly given by the tropical algorithm. And so that is, that's sort of the end of the story, right? And again, sorry, I did run out of time, as I promised. But like I said, let me say 2 things and wrap up. Thing 1 is the theorem is that the example generalizes. And the thing 2 is that when you see double Hurwitz number like this, you can actually generalize the notion of double Hurwitz numbers. The setup generalizes. Because if we think of the double ramification cycle as compactifying a locus of principal divisor of curves, what you can also do is you can sort of ask yourself a similar problem about loci of divisors that are that identify a line bundle, which is equivalent to some tensor power of the canonical bundle. And these are interesting geometric objects, but they don't have an interpretation as mapped to P1, so you don't have a branch morphism, so you don't have a natural algebra geometric enumerative problem, but somehow you get a natural tropical geometric enumerative problem. And so you get this really rich, interesting family of numerical invariants associated to these other geometric spaces. But that will be part of the next 2 weeks for whoever stays in Moraga. No, not true. We're all leaving. But yeah, thank you so much.